Hello and welcome to another power electronics class. In the previous class, we finished the single-phase full-wave AC voltage controller with a resistive load. So in a resistive load, because we don't have any storage elements, the voltage and the current would be matched. We don't have any phase shift. And we learned how we can measure VL, RMS, and the power factor, and so on. And as you can see here, this is V and the V and I, and they are synchronized. They don't have any phase shift because in a resistor, we don't have any reactive power. We just have average real power. And we can simply measure the power by multiplying voltage and the current. And we actually solve it for finding the RMS value and so on. Today, we're going to continue with the single-phase full-wave AC voltage controller, but with resistive inductive load, or RL load. And this would conclude the course for this part would conclude the course material. And if we have time, we can go through some exercises and some examples. And again, this is going to be the last course material that we're going to cover in this semester. Now, in reality, in practice, most of the loads that we have in real life are RL loads. We usually use this full-wave AC voltage controller for two main purposes. First one is to control an AC motor, and other times we use it for heating, induction heating. And both of these have an inductor or a coil. For example, if we want to control an AC motor has a winding, and that winding acts like an inductor. And we can represent that with L, which is the winding inductance of a motor. And the same thing for an inductor heater as well. So both of these usually have an RL load. And so we have an induction, which is the winding of the motor, or the inductance, and the copper, the wire itself. It's not an ideal copper. We have a little bit of resistor, therefore we have the resistance, or R, over there as well. So we would have two impedances. We have the inductance and we have the resistor. So due to this inductance in the load current IO flowing through T1 would not fall to 0 at omega t equal to pi when the input supply voltage starts to become negative. Why does this happen? Because the inductor acts like a storage element. It stores current in it. And what happens is it takes time for the inductor to charge, or to fully charge. And when it charges and you have current in it, when you disconnect it from a power source, it takes a little bit of time to discharge that current. So therefore, you're going to have a little bit of phase shift between the voltage and the current. So because of that, T1 will continue to conduct the load current until all the inductive energy stored in the load inductor L is completely utilized, and the load current through T1 falls to 0 at omega t equal to beta, and beta, where beta is referred to the excitation angle, and this is very important. Sorry, extension. Did I say? So the extension angle, or beta, for the resistive load was the same, but for a RL load, it's going to be, for the resistive load, it was the same as pi. For an RL load, it's going to be equal to beta. And we covered up to this point in the previous class as well. So for an RL load, if Vs is this graph over here, then I out, again, this is Vs, I out will look like this. I out would have a slight delay, and it will look like the red one. Now, here you can see there's also a difference between the amplitudes as well. Why do we have this difference between the amplitudes or of the current and the voltage? The difference between the amplitudes comes from the resistor itself. The shift in the phase comes from the inductor, okay? And we have this little bit of transition period, the alpha, or sometimes they call it the lambda. This is the switching time for the thyristor to turn on and off. And you're going to have a little bit of delay over here as well. So if we have Vs and we have the gate pulse coming in here, then I would have, again, a little bit of delay. This is IL, by the way, the I of the inductor. And therefore, the V out will look like this actually, and Vt will look like this. So you can see that here the energy would be the area under the curve that you have for Vi. So Vi would give us the energy over here, which is less than what we had for a resistive load. So in this graph, T1 conducts from omega t equal to alpha to omega t equal to beta. T1 then conducts the conduction angle for T1 is delta equal to beta minus alpha. Delta depends on alpha and the load impedance angle of phi. The discontinuous load current operation occurs for alpha greater than phi and beta less than pi plus alpha. So you can see that at this point, when alpha is greater than phi and beta less than pi plus alpha, we have the current passing through the circuit. And this is very important as well. Which is you can see it's a small shift from the voltage. Now, this circuit can be used to regulate the RMS voltage across the terminal of an AC motor or induction motor. It can be used to control the temperature of a furnace by varying the RMS output voltage as well. For very large load inductance L, the SCR may fail to commutate, and the load voltage will be a full sine wave. Again, because we have a very large inductance, you're going to have a very large phase shift in the system, and therefore you're going to have a full sine wave. A continuous load current and the output voltage waveform appears as a continuous sine wave, identical to the input supply voltage waveform for trigger angles alpha less or equal than phi. We lose the control on the output voltage, and thus we obtain V out would be equal to Vm over square root of 2, V out of RMS, which is exactly VRMS of a sinusoid. For the previous one, because it wasn't a sinusoid, it's a little different. Now, the RMS output voltage for the system for alpha greater than 5, the load current and the load voltage waveform becomes discontinuous. And what we need to do is we need to find the area under the graph to find the RMS or the root mean square of the voltage. For a sinusoid voltage, it's going to be Vm over square root of 2. For this, because it's a discontinuous system, it's going to be Vm over square root of 2, 1 over pi beta minus alpha plus sine of 2 alpha over 2 minus sine of 2 beta over 2, all of that in square root. Now the output current for inductive load, again, the output current we need to find it during the conduction of T1. And again, we can find the area under the graph for this. The solution of the above differential equation gives the general expression for the output load current, which is of the following. So I out would be Vm over Z sine of omega t minus alpha, minus 5 plus AE negative t over tau. And the impedance Z is equal to square root of R squared plus omega L square. And you already know the load impedance, where it comes from. It's the imaginary part and the real part, the real power and the imaginary power, square root of that. So it gives us the magnitude of the impedance. Now, this is a very important equation. Phi is going to be equal to tan inverse of omega L over R. This is the load impedance angle, or the power factor angle of the load. I want you to write this down. And tau is equal to L over R, which is the load circuit time constant. At omega t equal to alpha, I out is going to be equal to 0 amp. Hence, I out would be equal to Vm over Z sine of alpha minus phi plus A1e negative R over LT. And when we simplify it by substituting the alpha equal to omega t, then A1 would be equal to AE R over omega L minus Vm over Z sine of alpha minus phi. Now, if we want to find the instantaneous output current, we can use the equation. I out would be Vm over Z sine of omega t minus phi minus sine of alpha minus phi e negative R omega L over omega L omega t minus alpha. So this expression represents the thyristor's current as well, IT1, and it's during the conduction mode, the conduction time of the system. And in the conduction time, the angle is between alpha and beta. You can see that this is the conduction time between here and here. Now, to calculate the extinction angle beta, to be able to calculate the instantaneous current or the thyristor current, we want to find omega t at beta and I out at 0 amps. Why do we find I out as 0 amps? Because again, when it reaches beta, I out would be 0. So you can see that at this point, I out becomes 0 at omega t equal to beta. And we had it here as well. At the point beta, omega t beta, or pi plus beta, the same. I out would be equal to 0. Now we will replace the equation above with 0, and assuming that Vm over Z is not 0, sine of beta minus phi would be equal to sine of alpha minus phi e to the power of negative R over omega L beta minus alpha. Now beta can be determined from the transcendental equation by using the iterative method of solution, trial and error method. So this part is a little tricky when you want to solve some practice problems. Now for delta less than pi and for beta less than pi plus alpha, the load current waveform appears as a discontinuous current waveform. When alpha is decreased and made equal to the load impedance angle, or in other words, alpha is equal to phi, we obtain from the expression for sine of beta minus phi would be equal to 0. Therefore, beta minus phi would be equal to pi on radians. So for the extinction angle, beta would be pi plus phi or pi plus alpha for the case when alpha is equal to phi. And for the conduction angle, delta would be beta minus alpha, which is 180 degrees, or pi in radians. For the case when alpha is equal to phi again. So each thyristor conducts for 180 degrees, or p radians. T1 conducts from omega t from phi to pi plus phi, and T2 conducts from pi plus phi to 2 pi plus phi. Now again, this is a proof for the graph that we had here, and you can see, let me delete this one. So you can see here that it is conducting for 180 degrees if you start from here. And one thyristor is conducting for 180 degrees, and the next one is conducting for the other 180 degrees. So each of them is conducting in one half. One is conducting the positive, the other one is conducting the negative. Obviously, when they are in parallel, you can see, let me bring up the graph as well, the circuit diagram as well. So one of them is conducting in the negative cycle, the other one is conducting in the positive cycle, and each of them is conducting for 180 degrees. Now for a resistive load, I want to just go back. It starts conducting from 0 to pi maximum if we wanted to do, if we didn't have a trigger angle or a turn on angle, fire angle. And the other thyristor would conduct between pi and 2 pi. But for a RL, it's a little different. We have a little bit of phase shift, which is alpha over here. And it starts conducting from alpha to pi plus alpha. And again, for example, from pi plus alpha to 2 pi plus alpha. So therefore, this is important part again. Where is it? This two parts are very important, and you may have it in your exam. So for an RL load, again, T1 conducts from omega t equal to phi to pi plus phi, and T2 conducts from pi plus phi to 2 pi plus phi. And each of them conduct for pi radians or 180 degrees. The extinction angle is beta, which is pi plus phi, and the conduction angle is delta, which is beta minus alpha. So from this, we can obtain the continuous load current, and the output voltage waveform appears as a continuous sine wave identical to the input supply voltage 4. So output voltage is going to be sine wave identical to the input voltage, but the current, as you saw, we have a phase shift and a little bit of distortion in it. Now for performance parameters to find the load current, output power, RMS voltage, we can again use the calculate the output RMS by calculating the area and therefore the root mean square of the voltage. And for this case, V out RMS is going to be Vm over square root of 2, square root of 1 over pi beta minus alpha plus sine of 2 alpha over 2 minus 2 beta over 2. And the load current is going to be the same that we had previously. I out would be IT1, which is Vm over Z, and the rest that we had before. Now the average current, we have to find the integral of this to find the average current of this, and the average current would be 1 over 2 pi, the integral of alpha to beta, I of T1 d omega t, and we replace I of T1 with the equation that we had here, and we get this equation. Now, to simplify it, IT average would be Vm over 2 pi z integral of alpha to beta sine of omega t minus phi d omega t minus sine of alpha to beta sine of alpha minus phi e power negative r omega l omega t minus phi alpha. By the way, I will provide you with all the equations necessary in the exam. You don't need to memorize any of that. So the maximum value of IT average occurs at alpha equal to 0. The thyristor current should be rated for maximum IT average, which is Im over pi, and this is very important, where Im is equal to Vm over Z, Ohm's law. Now the RMS current of the thyristor would be equal to square root of 1 over 2 pi integral from alpha to beta IT1 square d omega t, and the maximum of IT again occurs at alpha equal to 0, and the thyristor should be rated for maximum of Im over 2. Now the maximum average of the thyristor was Im over pi, but the maximum rated current of, which is the RMS current of the thyristor, is Im over 2. Now, if we use a triac instead of a thyristor in a single phase full wave AC voltage controller with RL type of load, then the average triac current would be 0, and the maximum would be Im over square root of 2. So only difference between the triac and the thyristor that we have. Now, let's solve an example. Again, this example is like 90% similar to what you're going to have on your final exam. We have a single phase full wave AC voltage controller which supplies an RL load. The input supply voltage is 230 volts, RMS at 50 hertz. The load has an inductor of 10 millihenry, a resistor of 10 ohms. The delay angle of SCR1 and 2 are equal, meaning they would fire at the same time. The delay angle that we have between these two are equal. Therefore, the delay that we have, these deltas are also, these lambdas are also the same. And alpha 1 is equal to alpha 2, which is pi over 3. We want to determine the conduction angle of the thyristor, the RMS output voltage, the input power factor, and we want to comment on the type of operation. So we are given Vs is 230 volts, frequency is 50, L is 10 millihenry, R is 10 ohms, alpha is pi over 3, which is 180 over 3, which is 60 degrees. And alpha 1, alpha 2, alpha are all going to be equal to pi over 3, which is 60 degrees, by the way. Now, Vm is going to be square root of 2 Vs, which gives us 325.2691193. Why did we use this equation? Because the voltage, as mentioned, is going to be a sinusoid. And for a sinusoid, Vm is going to be square root of 2 Vs. If we didn't have a sinusoid, it's going to be completely different. Now, Z is going to be load impedance, which is, again, the equation that we use. It's going to be R squared plus omega L squared. And omega is 2 pi F, as you know. So omega is going to be 2 pi FL, which gives us 2 pi times F was 50 hertz times L was 10 millihenry. So 10 times 10 to the power of negative 3. And therefore, this gives a 2 times 50 is 100. 100 times 1,000. I'm sorry, 100 times, and this is 10 to the power of negative 2, times 10 to the power of negative 2 gives us 1. So we are left with pi, which is 3.141. Now Z would be equal to 10 square plus 3.1415 square. And the impedance is 10.4818. Now, why do we need this impedance? Because IM is going to be equal to VM over Z. We already have VM, which is 325.269. So 325.269 over 10.4818. This gives us, yeah, and by the way, if I want to find IM, I can do square root of 2, times Vs or Vm over Z. So let me see if it's been solved here. Yeah, so IM would be Vm over Z, and Vm from the previous one we had, this part was 325.269 divided by Z, which is 10.4818, gives us a current of 31.03 amps. Now the load impedance angle, as I mentioned, this is important equation. Phi is going to be tan inverse of omega L over R. Omega L, again, what was omega? It was 2 pi times 50, and L was 10 times 10 to the power of negative 3. It was millihenry. So again, these is going to be 10 to the power of negative 2. This is going to be 100, so we're going to be left with pi. Now it's going to be tan inverse of pi over R was 10. So it's going to be 0.31, tan inverse of 0.314, which gives us 17.44059 degree. Now the trigo angle, alpha must be greater than phi, hence the type of operation will be discontinuous load current operation. We get for beta less than pi plus alpha. Now beta would be less than 180 degree plus 60, so beta should be less than 240 degree. Therefore, the range of beta is from 180 degrees to 240 degrees. Now, the extinction angle B is calculated by using the equation here, okay? Now, we know that beta should be between 180 degrees. Let me write it here. Beta should be between 240 degrees and 180 degrees. Okay, so greater than 180 degrees and less than 240 degrees. But we don't know exactly how much is beta. So we have to try use this equation and use a try and error method to be able to find it. We have to find the right-hand side of the equation and the left-hand side equation and be able to match them, okay? So we would put random degrees. We would, for example, for 200 degrees and 190 degrees. If 200 degrees is imbalanced, then we go lower. If 180 degrees is imbalanced, we go higher. So we have to try different numbers until we match that. So in exponential term, the value of alpha and beta should be substituted in radians. Hence, sine of beta minus alpha would be sine of alpha minus phi, e in the power of negative r over omega L, b in beta in radian, and alpha in radian. And alpha in radian is pi over 3, as we already know. Now, alpha minus phi would give us 6c minus 17.4405, which is our phi, which we got again from this equation. And that gives us 42.559. Now, we will find sine of beta minus this and the sine of 42.559 e in the power of negative 10 over pi beta minus alpha. And when we solve this, assuming beta is 190 degrees, we see that the left-hand side is going to be equal to 0.12948, and the right-hand side is going to be 4.94 times 10 to the power of negative 4. These two are way apart, so we have a huge difference. What we're going to do, we're going to assume another beta. We're going to assume that beta is now 183 degrees. So this is previous time. How much was it? It was 190 degrees. Now we would assume a little lower, close to 183 degrees. And when we solve it for 180 degrees, the left-hand side, this is important, would be 0.24936. The right-hand side would be equal to 7.2876. So we went further apart. So we shouldn't reduce the angle. We have to increase the angle to get these two closer together. Okay. So for 190 degrees, again, when we simplified the equation, by the way, we simplified the equation with this, and we just replaced this beta. I'm sorry, where did I go? Yeah, we simplified the equation to this. And the difference was between 0.1 and 0.004.94. And when we reduced the angle, we went further apart. We made it even worse. Now, the third time, we would assume that beta is 197 degrees. And by solving the left-hand side of the equation, we get 7.67937. And the right-hand side would give us 4.9503. So now we see that we're getting a little closer. Now increasing it a little bit to 197.42 degrees. And by the way, these two are very close to each other. We get the left-hand side to be equal to 3.4906 and the right-hand side to be 3.2709, which is very, very close. And one thing, to be able to calculate these manually, it's going to take a long time. We have simulation tools like MATLAB and other simulation tools that automatically simulate and give it like 100 different angles, between 180 divided to 100 different angles and 240. So every 0.1 degree angle, it would calculate them, create a graph, and you can see it. Manually doing it, it's going to take a very long time. Now, the conduction angle delta would be beta minus alpha. So beta, we calculated to be 197.42 degrees. And alpha was 60 degrees. So this gives us 137.42 degree. By the way, in the exam, I would usually provide beta. So you don't have to calculate beta, but you need to do the rest, which is the easy part. Now, V out RMS, we use the equation that we had, which is Vs square root of 2 over 1 square root of 1 over pi beta minus alpha plus sine of 2 alpha over 2 minus sine of 2 beta over 2. And when we calculate that, V out RMS is 207.0445. And the power factor is going to be the real power over reactive power over the apparent power that we have over P over S. And it's going to be equal to V out over Z, which is 207.04 over 10.48, which gives us 19.7525. Now the output power is going to be I square RMS RL. We have I as 19.7527 in the power of 2 times 10 gives us 3.9 kilowatts. And Vs is going to be 230, and Is is I out RMS, which is 19.7527. Therefore, the power factor, we can find that by dividing P out over Vs Is, which gives us a power factor of 0.8588. Again, all the equations would be provided in your final exam. So these 3 exercises, we are done with our course, I would post them as your next homework. I would highly recommend that go and try to solve all of them by your own and try to think on them. And it's going to be the same thing that as the previous exercise. Only the numbers have changed, and you're going to have at least 2 of these exercises, exactly 2 on your final exam. I won't even change the numbers. 2 of these exercises that you're going to solve on your homework would be exactly reflected on your final exam as well. So that's it for our course. We are done with the power electronic course. As mentioned, the next class would be a review session for the final exam. And if you have any questions, just please email me. And thank you so much. I'll see you next class.